This is Algebra 2 with Trig. This is the review for the 7.1, 7.4 quiz. We're looking at an exponential equation. It's been translated 3 units to the left and 5 units down. To help us figure this out, we're going to start out with the parent function, which is just the base to the 4th power. So 4 to the 4th power, 4 to the x power. When we plug in -1, we're going to get 1/4. Plug in 0 for x. Anything to the 0 power is 1. Anything to the first power is 4. Anything, well, 4 to the first power is 4. 4 to the second power is 16. So we could graph that. When x is -1, we're at 1/4. X is 0, we're at 1. At 2, we're at 16. I'm doing well. So that's going to become y equals 4 to the x power. That has an asymptote at 0. We won't put down that equation, but we want to be sure that we understand what's happening. We now know that there is a translation where h equals -3 and k equals -5. So we're going to take each of those points we found and move to the left 3 and down 5. So we'd have an asymptote at y equals -5. This equation would then be 4 x plus 3 minus 5. The domain, what x values could I possibly plug in for it, would be all real numbers. For interval notation, that would be -infinity to +infinity. The range, what values of y could I get? My values of y after the translation would be greater than -5, which in this case would be -5 to infinity. The end behavior. As x moves, what's the smallest value x can be? X can be negatives, it can be positives, it can be all the different values. So -infinity, as it moves to the left, the function approaches -5. It gets closer and closer to -5. As x moves to the right, as it moves to +infinity, the graph also moves to +infinity. It goes upwards as x gets bigger. For number 2, we're going to write an equation, growth model. Write a growth model. We're not solving for anything, we're just writing the model. So in 1995, about 900 students at PCEP owned a cell phone. Over the next many years, about 12% more students owned a cell phone. The more indicates that this is a growth function. So we're going to use the equation a 1 plus r to the power of t. So we have 900 students, 1 plus 12%. 12% would be represented as a decimal as 0.12 to the t. We don't know how many years. We're not trying to calculate. We're just trying to write a model. So another way we could write this would be 900, 1.12 to the t. You have 100,000 hairs on your head today. The average person may lose, which is decreasing, about 2% each year. Write a model given the number of hairs on your head after t years. You're still going to use that formula of a 1. This time it's going to be minus r to the t. So we're starting with 100,000. 1 minus 2% would be 0.02. So we could write this as 100,000 0.98 t. Now we're going to use that model to calculate the number of hairs on your head after 12 years. So we'll take the 100,000 0.98 for the years of 12. So we'll bring in our calculator. We have 100,000 0.98 raised to the 12th. That gives us 78,471. And I'm okay with you putting down a decimal just to show that you got the exact value that we would expect. And that would be hairs. The value of a baseball card can be modeled by this equation, where t is the number of years since a baseball card was produced. What is the initial value? Well, here you could tell the initial value would be $45. Is this an example of exponential growth, or is it decay? Because what we're multiplying by is greater than 1, we have exponential growth. Because the b value is greater than 1. What is the percent of increase? The percent of change. So what is your r? The r value would be 0.08 or 8%. 8% would be the best answer because it is asking us for a percent. On the other side, you deposit $8,125 in an account that pays 3.35% annual interest rate. Find the balance after 12 years if the interest is compounded weekly. We know that there's 52 weeks in a year. So using our formula, we're going to start out with our 8,125. 1 plus, our rate of change is 0.0335. Our n value, which is how often it's compounded, is 52. So that means we're going to take our 3.35 and we're going to break that into 52 equal amounts. So we divide that by 52. And that's how much we get at the end of each week. So by taking that 52 and multiplying it by the number of years, that also tells us how many of those weeks there's going to be in this calculation. So we get our calculator, and we can say, what is 1 plus 0.0335 divided by 52? We want to be sure that we're dividing just the 0.0335. So that's going to be 1.0006. And 52 times 12 comes out to 624. Now, if we want to find the balance, then we would take the 8,125. I still think that you should do that calculation, 0.0335 divided by 52, just so we're doing the calculation of the real number, raised to 624. If you used a rounded number like 0.0006 and didn't use the official value, you would get a little bit different answer. $12,143. So it would go up by almost, or a bit more than $4,000 just for sitting in an account. That would be pretty nice. Let's see what would happen. I'm just curious now. 8,125 times 1.0006. If we use that rounded number 624 times, you see that would be a considerably different answer. So you want to be sure that you use the real answer and not some rounded answer when you're finding your calculation. Now we're going to graph this function. This is also exponential. Since the b value is less than 1, we know that it is going to be a decay. The parent function is 2/3 to the power of x. When x is a negative, we get the reciprocal, which is 3/2. When x is 0, we always get 1. When x is 1, we always get the number that's there. X is 2, we're going to square the top and square the bottom. So this fraction here, this is 0.666. Whenever you're dividing by 9, it would be the top number, 0.4444. Just to give you an idea of where that goes. At -1, we're up at 1.5. At 0, we're at 1. At 1, we're at 0.6. At 2, we're at 0.4. So it looks like it's getting closer and closer to the x-axis. Now, when we had, just to give us some more ideas of what's happening with our graph, when x is -2, we would flip that over and get 3 halves. and then we would square both of them to get 9/4. And 4 goes into that 2 1/4. So you can, you can see that it's growing pretty slowly. At -3, it would be 27/8, which is 3 3/8. So it's not growing that fast. So that's our equation. Y equals 2/3 to the power of x. That's our parent function. Now we're going to take each of those points and we're going to move them 2 to the right and 3 down. H is going to be 2 and K is going to be -3. So be sure to follow right along with where the asymptote would be. We should have the asymptote right there at y equals -3. This equation is y equals 2/3 x minus 2 minus 3. So the domain, what numbers could you possibly plug in there? That would be all real numbers, from -infinity to +infinity. The range are all the values that are greater than -3, -3 and up. The end behavior, as x gets really small, the function's getting really big. When x gets really big, the function is getting super close to -3. Here we'd say e 6 plus -4, which is e squared. Here we have the cubed root, 24 divided by 3, and e -9 e cubed. So we could say 8, and that e would come down to the bottom, so that would be e to the 12th. Now what is the cubed root of 8? 8 is broken down into 2 times 2 times 2. So the cubed root of that would be 2. What is the cubed root of e to the 12th? Well, e to the 12th would be 12 different e's in groups of 3 at a time. That would give you 4 of them, 4 groups of 3. And they would be in the denominator. Here you would square the exponent and square the, or not square, sorry, we're going to multiply. Multiply the exponent and multiply the exponent. So 1 is your exponent, so 2 times 1. negative 6x. So your answer is going to be 4. The e has a negative exponent, so it goes through the denominator. You deposit $3,020 into an account that pays 5.75 annual interest rate, compounded continuously. So the compound continuously formula is the Pert formula. A equals P-E-R-T. The R and the T are exponents. So A is the amount that's in your account. P stands for the initial amount, which is 3,020. The Pert formula uses the letter E. R is your interest rate, 0.0575, and T is the number of years. So we're going to use 0.0575 times the number of years, which comes out to be 0.5175. That's just to show some work. Now we take our equation. That's an exact value, so I don't have to worry about rounding work or anything. Now I'm going to get 5,067.04. And that would be money. So I can put a dollar sign with it. The last page, write the equation in exponential form. So remember, we do 2 to the 6th power is 64. So 2 to the 6th power, that would be exponential form. 9 squared is, of course, 81. And 1/3 to the negative 3rd power is 27. The negative would flip the fraction over to make it 3, and 3 cubed is 27, so that works. Evaluate. So that's our unknown. So 9 to what power equals 81? Well, 9 squared equals 81. So we know to evaluate that logarithm, it would stand for 2. 1/3 to what power equals 27? Well, you would have to flip the fraction over to make it 3. So we know that it's negative. And 3 cubed makes 27. That's just like the problem we did above. Another way you can write this is, how can you make 16 have the same base as your logarithm? So 2 to the 4th power. Now the 2's are the same. So the value is your exponent, which is 4. Find the inverse. To find the inverse, the first thing we need to do is switch the x and the y. Then we need to solve. So to solve for y, we would have to use a logarithm. The base is 4 of x equals the exponent. A logarithm always equals the exponent. These are considered inverses of each other. So we interchange the x and the y. This time we're in logarithmic form. So the inverse should be exponential. So I'm looking for the base of ln, which is a natural log. The base for ln is e. A logarithm always equals what the exponent is. Then we subtract 8. Start by switching your x and the y. This is currently a logarithm, so its inverse is going to be exponential. So we take the base, we take the exponent, and it equals y. Remember, the logarithm always equals the exponent. So since the log of base 4 of y equals x, we know that x is the base, is the exponent for 1/4. We're going to graph the function. We're going to make a table for the parent function, and then we'll make our graphs. So the parent function is y equals log of 5x. So for us to actually figure out what the log base 5 of x is, we would say 5y equals x. And we're going to pick values for the y. So -1, 0, 1, even if we pick 2, it would be fine. -1 is going to make it a fraction. 0 makes it a 1, and 1 makes it a 5. Anything bigger than that, it's going to grow very quickly. So when x is really small, 1/5, like 0.2, we're going to be down low. Then we're at 1, 0. Then we'd be at 5, 1. Then we'd be way out at 25, 2. So for this equation, I know that we have y equals log base 5 of x. We have an asymptote that's following the y-axis this time. We don't label it until we get to our final graph. So we're now looking at this equation. It has a translation. It is a translation where h is -4 and k is +3. So we're going to take all the values wait a minute here. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. These are all in the wrong spot. 1, 2, 3, 4. 1, 2, 3. So be sure to understand that the graph isn't actually going straight down. It is slowly but surely always falling to the left. But we have an asymptote here at x equals negative 4. It's x because it's a vertical line. Our equation is log base 5 of x plus 4 plus 3. The domain, what are the x values? How far left could we possibly go? We could only go up to negative 4. So we know our x values are greater than negative 4. Or you could say negative 4 to infinity for interval notation. The range, what values of y can we possibly get? We can get negative values of y, positive values of y. So now we can get all real numbers. We go down forever and we can go up forever. It just takes a long time for it to get up. The end behavior. As x moves to the left, how far left could it possibly go? It can only go to negative 4. What's happening as we move closer and closer and closer to negative 4? The graph is going down. As x moves to the right, which is positive infinity, the graph is also going up, just not quite as quick.